Okay, now I want to start a mechanical example. This can be found in our Moodle course in the paper exercises on the one of the first pages in the exercise 1.1. There is a task text which I have copied now into my system here, and this is a picture with information function, and these are the equations. So what happens here? This is a tank, say with water, with an outlet, and this is the outlet flow QA, which is unknown, which is dependent on things we cannot influence. So this output, maybe this is the water supply for a small town, this is a water tower, and this is the water going to the houses, and the outlet depends on the water consumption of the single houses. So unknown. The goal is to have the same pressure here. The pressure depends on the height of the water, so the height should be constant. So if there is a water consumption, the level of the tank goes down. And to control now the level, this is a tank level control, here you can see a mechanism which should control the height of the water to the desired value y sub o. This is done by a swimming ball connected to this lever. This is the lever which grounding point here of the axis here. So if this goes down, this goes up. And the lever opens here a valve. Here is a big water reservoir which can refill the tank by the input flow QE depending on the valve. The larger this value Z, the more the QE is increasing. So the more this goes down, the more this opens, and then you have an input flow QE. The physical laws are very simple. First, we have three equations. One equation here is the valve equation. The input flow is a valve constant multiplied with the size of the increasing of these lengths Z. The larger Z, the more QE. So this is a proportional relation. That's of course in real valves we have nonlinear behaviors. This behavior is linear, so in first order we have linear systems. Okay, that's the first law. The second is a lever law. The Z over LZ is the same as H over LH. So this is the lever law, just a proportional behavior, that this is proportional to this. The H value is proportional to Z value. Okay, and the final equation is here the the content of the tank. The content of the tank is just base area A times height. Height is, the actual height is Y, desired height is Y sub O, and here I want to calculate the difference to the desired value and call this difference H. If H is 0, then we have reached our desired value. If H is positive, you see the tank value goes down. So the content is just base area times height, and the actual value of Y is desired value minus the actual value of H. And we can, on the other hand, we can say the content is a starting content value, say 1000 liters or so, decreased by the output flow integrated over time, increased by the input flow integrated over time. So the integration of the flow difference gives that volume which is added or subtracted to the starting level Y sub O. task. We want to have the signal block diagram of the system, and you will see if I do this in the end of this task, you will see this looks very similar to the single loop control loop system, standard loop, what we have discussed in previous sections. Okay, first is we have, if you want to have the block diagram, we have to find out what is input and what is output. That is not so trivial in this system, because normally the first answer is output is this QA. That is of course the output of water, but not the output of my dynamical system. For the output we can very simple say output of a control system. This is a control system. If that what is controlled, if you go back to lecture number 1, this is my output which is controlled. This is the speed control. Then we have other examples: distance control or blood sugar control. So we have the output of a closed loop system. Is that what you want to control? So we can say the output is H. That is the tank level. H tank level. If you are not sure, we can very simple say, okay, the output of a closed loop system for a temperature control is the temperature. Output of distance control, distance. Output of concentration control is the concentration. That is the output which has the most interest. So we want to have our signal block diagram with exactly tank level as output. So we can say, okay, our signal block diagram has an H, capital for frequency value, as output. What is the input? Is there anything which can be influenced from the outside, or is this, which value is dependent? We can say, okay, if H is the output, Z depends on H with the lever law. QE depends on Z with the valve law. And and the H value is depending on QE minus QA. Okay, and what I have told you is QA is an unknown value which we cannot influence. So we can say QA is an input. QA of T, or we want to, the convention is that we want to draw frequency functions with uppercase letters in our signal block diagram. QA is the input signal which can influence my system. Now you can ask, okay, closed loop system can have here an input desired value and an input disturbance value. What is QA? Of course, a disturbance. Where is the input for the desired value in our closed loop system? Very simple. The answer is there is no input. The desired value is fixed of H with the value H is 0. Why? 0 is my desired value. We cannot change, so there is no input. No input for desired value in this situation. Just a hint, a question. This is a mechanical closed loop system, and what we know about this principle is that the eldest closed loop system, artificial closed loop system, which we have found in the world. And if you ask how old is this, then the answer is very simple. The old Egypt has used exactly this structure to control the level of a tank, which they have used for a water clock. They used this tank with a very small outlet with drops coming out of the water to have a time base. in 3,000 years ago. Yeah, this time base was important for some investigations over they have done in the old Egypt state, and they have found out that the drop rate depends on the pressure. The pressure depends on the height, so they have exactly built in this principle to have the level constant, to have a constant drop rate. So the eldest closed loop system we have found in the world. And of course, you know this principle, you can find this in any water toilet. That is just the mechanism to fill the tank for cleaning of the toilet. Yeah. Okay, back to our task. Back to the setup of a signal block diagram. So the input is QA. That should be Q. So QA, and output is H. And now the strategy for setting up a signal block diagram is very simple. Take the equations, convert them into frequency, domain, because we want to write down here the block functions in frequency functions, not like this integration. So we can first say the first equation is QE, uppercase Q for frequency function is wave constant times capital Z. That is a frequency function. So a multiplication in time domain is of course a multiplication in frequency domain. So the conversion of a linear equation is very simple, just a copy and replacing lowercase letters with uppercase letters. LZ of course is a constant, and H is the dynamical variable, and LH is a constant. It's the second equation, second, and the third, we put this together. The third equation is the following. You see the left sides are equal, so the right sides also must be equal. On both sides we can find 8 times y0. Here is 8 times y0. So on both sides we can subtract this. So on the one side we have a negative h of p. This one on the one side, and this integration is then on the right side. The result is, and the integration in frequency is nothing else than a multiplication with, oh sorry, I have forgotten the a. The a times minus h is minus a times h, and on this side we have an integration. 1 divided by p is the replacement of integration, multiplied with the difference QE minus QA. So these are the three equations we now use for setting up the signal block diagram. The strategy is, after defining output and input, starting with the output side, going backwards, finding equations containing H, then finding equations containing the open inputs, and so on. Yeah, like we have done it in our RCE circuits. H of P, so I start with the third equation. Of course, I could also start with the second equation because this contains also an H, but I today prefer the third equation to starting equation, because then I get a signal block diagram which fits to our closed loop system. Yeah, H on both sides I divide with minus A. H is minus AP. This is a block function. Minus 1 divided by A times P, and the input of this block is the difference of these two flows. One flow is here given as an input, so I can connect directly with the summing point. QA is negative. I have to add a negative sign. Output is connected to my input. And the second input here is the QE value. QE. So the first equation I used is the third equation in my list, and this is the drawing of this equation. Now we have an open input QE, so I need an equation where QE comes out. This is given here in equation 1, and I can at once draw this block. QE is the output, C is the wave constant, input is Z of P. And finally I have a second equation. I can put also this second equation and solve this equation in respect to Z. Z is H times, H is the input, times LZ over LH. So we have here a constant LZ over LH. And H is available as output. So I can directly connect this output with this open input. That's what I can find. Note, if in my setting up a signal block diagram I have this following situation, say H, and I have another situation where I have also used an equation with an output H, then I have a problem, because two outputs with the same value cannot be connected. So this is wrong. Never use two equations in that way that both equations produce the same output. Then I cannot set up a signal block diagram properly. Never use equations with the same output. It's a contradiction. This gives H, this gives H. You cannot combine them with the same output. No, only have one element with output H, then you have an open input, then look for equations which have this open input value as an output, connect them. Then we have a new open input Z, look for an equation which has Z as an output, connect them, and then this step by step can fill the signal block diagram. Okay, if we compare this signal block diagram with our standard loop, then this looks different, especially because the disturbance here is drawn in that way and not in that way. So with a redrawing of this plan, I use unchanged block here, 1 over negative 1 over AB with output H. Input is the summing point. Then I draw this not from right to from left to right, but from top to down. This is QA with negative sign, and then I shift this block and this block in that way to this position. Just a position change, not a change of the signal block diagram. The signal block diagram is really the same, and this is LZ over LH. This is Z, and this is the wave constant C, and this is the QE value. Then I have to close my loop, and I add now a summing point, which is not here, a new summing point, but now with my connection. One input of the summing point is my H, and the other input could be the desired value. In our case is a 0. And the summing point where one input is 0 is really can be extinguished, can be deleted. I have added this summing point so that you can see really there could be a change of the desired value, and this is just very similar to my standard control loop. Compare with standard control loop. Compare with standard control loop. You can say, okay, this is a process, a tank. 1 over P comes from the integration, and here we can say in general this is an integrating process. This is the actuator, and this is the controller. Desired value is not available. This is a disturbance. Question: where is the minus sign? Is this loop a negative feedback or a positive feedback? We can answer this if we first see this minus sign, but this minus sign is not a minus sign in inverter within the loop. That is just an inverter for the input signal. So this has nothing to do with if this is a positive or negative feedback. Here is the plus sign, but negative feedback we have in any case if there is one minus sign in the loop. And you see here the process has a minus sign caused by the equations. This minus sign gives the negative feedback, so this system really works. And you can believe me that this works because this works in every water toilet. Yeah, so you can see, okay, my standard loop has no input for desired value. Here we have a disturbance input. Here we have an integrating process. Okay, one last word is this is a constant factor LZ over LH is depending on the ratio of the both lengths to the axis. A constant factor is a proportional block. Later we will call this P block, and we can generally say this is a P controller. The P actuator is also a constant with an integrating process with a disturbance. Disturbance. And the behavior of this loop with the P controller and I process is typical for any other loop which has a P controller with an I process which is disturbed by a disturbance. Okay, so far you see, independent if this is an electronic circuit or is a mechanical system. This is a mechanical system, or maybe this is a pneumatical system or chemical system or medical system. We can convert, we can look for equations, physical equations, and then convert these equations into this loop, and then we can have for any of these areas of loops, we can now have the same methods to analyze signal block diagrams, to calculate step responses, Bode plots, and so on. If we have the signal block diagram, the rest, what we now do in control system, is independent of the kind of the area. So the signal block diagram is a very good interface between different areas to our control system theory. So far, in the next video, I show you a simulation program where we can simulate this system with a simulation program.